Welcome back. Today we're going to look at how to compute some probabilities from familiar distributions. I'm going to share my screen. Okay, go to Matlab. Now, the nice thing about Matlab is it allows you that if you know the distribution of your data, you know the shape of that distribution, you know its parameters, it can compute probabilities for you. Likewise, if you know the probability and you know the distribution, it'll compute the value of the distribution, the critical value for that probability. So let's start with the normal distribution and we'll go from there. So let's suppose we want to find out the probability of getting exactly the mean from the normal distribution. Let's call it the standard normal distribution, a normal distribution with a mean of 0 and a standard deviation of 1. So you can use the norm PDF. Okay, that's probability density function with the normal distribution. And we are going to find out what the value, okay, what the probability of, let's say, 2 sigmas above the mean, okay, that's plus 2, given a mu, okay, of 0. That's the center of the standard normal distribution, and a sigma of 1. That's the standard deviation of the standard normal distribution. And it says the actual probability of getting exactly 2. You take all those infinite number of values and get exactly 2, pulling that out of a population that has a mean of 0 and a standard deviation of 1 is about 5%. Okay. Let's find out the probability of getting exactly the mean. Okay, so instead of 2 sigmas, this is going to be 0 sigmas, exactly at the mean, same distribution, and it's about 0.4. Okay, what you see in all the graphs in the book. Okay, so the probability of getting exactly the mean, pulling the mean out of a standard normal distribution, is exactly 0.3989. That's the probability of getting exactly 0. The probability of getting, let's say, negative 2, okay, and we know it's about 0.05, so it should be about, okay, about the same, right? Because of the symmetry, it's exactly the same, right? It's symmetric. Okay, all right, so that's norm PDF. It'll give you exactly the probability in the probability density function. Most of the time, you're not going to be using this distribution because you'll be wanting to compute cumulative probabilities across a region, an interval in the distribution. So the Matlab function for that is norm CDF, right, for the normal distribution. Okay, and let's find out what the cumulative probability of getting 2 standard deviations above the mean, given a normal distribution with a mean of 0 and a sigma of 1. Okay, and now we'll hit enter. Oh, did I put the colon in, and so it put it up in the workspace. So here it is. So it's about 98%. Okay, so the integral from negative infinity to 2 standard deviations above the mean is about 97.7%. Okay, now I always tell you, it's about 95%, right? Well, this is about 95%, but if you want it to be exactly 95%, you would have to find the value of 1.96. Oh, excuse me, not 1.96, 1.64. Okay, 1.64 gives you exactly 95%. And 1.96 gives you 2.5%. Again, we haven't changed the parameters. It's a standard normal distribution. All I'm doing is changing the value, and it's computing it's integrating from negative infinity up to, in this case, 1.96. And you can see that that gives us the 2.5% in the tail and the 97.5% in the left-hand part of the distribution. I don't have to be above the mean, right? I can say what's the probability, the cumulative probability of getting negative infinity up to negative 2 standard deviations. And you'll see that's about 0.0540. Okay. So you can use this very nicely. Now, you also don't have to use the standard normal distribution. We could use the distribution of IQs. So we know that IQ has is distributed as normal because they force it into that distribution. It's a terrible idea in general that people can be ranked by global intelligence when people have so many different talents and abilities. But people do it. It has a mean of 100, and it has a standard deviation of 15. So now we've just got a normal distribution as a mu of 100, a sigma of 15, and I want to find out what the probability of getting an Einstein is. Okay. Now, remember, Einstein had a IQ they estimate at 160. Okay, so I'm going to just put 160. So this is going to integrate from negative infinity to 160. It'll give me the cumulative probability of getting of randomly drawing from the population anybody who has an IQ either 0, okay, dead, all the way up to 160. So what we're really interested in is 160 and above. I can show you how that works. And we'll say, it says, it's so unlikely to get above 160 IQ that Matlab can't even compute it, right? If we take a look at the standard deviation, 160 is 4 standard deviations above the mean. Okay, so highly unlikely that you would ever, at any point in time, reach into a population of human beings and get another Einstein if you believe that intelligence quotient is a good measure of Einsteinism, right? Okay. Now let's do something a little more. What's the probability of getting, let's say, exactly 2 standard deviations above the mean? Okay, 2 standard deviations above the mean in the standard normal distribution. Let's do 130. That's 2 standard deviations above the mean in this distribution, and you'll see that it's exactly the same, 0.9772. All right. So the probabilities, the standard normal distribution is just any normal distribution that's been rescaled. So the probabilities, if I'm 2 standard deviations above the mean, it's the same as being 2 standard deviations above the mean. Okay, so we can compute those probabilities very easily, no matter what the parameters are. If you know the parameters and you know the value, you can compute its cumulative probability. All right. Now, we can also go backwards. If we know the probability we want, we can find the critical value of the distribution. And that's where we use ICD-F, okay? And we have to tell it the name of the distribution. Okay. This is a normal distribution. And we want to know the probability. Okay, the probability, let's find the probability at exactly 0.05. Okay, and then we have to give it the parameters. Let's call the parameter, the mean is 0, comma, and the standard deviation is 1 in parentheses. So this says, give me the inverse cumulative distribution function. Okay, this gives me from a probability that's known, okay, in a distribution that has these a normal distribution that has these parameters, a mean of 0 and a standard deviation of 1, I want you to compute the value that corresponds with a cumulative probability of 5%. And it's negative 1.6449. Okay, so if I integrate from negative infinity to negative 1.6449 to 1.6 standard deviations below the mean, I will get a cumulative probability of 5%. Now remember, the normal distribution is symmetric. So if I subtract that 5% from 1, I get 95%. Okay, and I'm just going to put 95% in there. Exactly the same parameters. Okay, I get positive 1.6449. Okay, so if I integrate from negative infinity to 1.6449, I will get a probability of 95%. So anything above 1.6449 is in the rejection zone, okay, for a right-tailed test, and anything to the left of it is in the confidence interval. Okay, so we can compute critical values very easily from this. If I want to compute the critical value of the normal distribution that has let's just go back to here. Let's go 115 back to IQs, and I want the 95th percentile. There, that's the 95th percentile. If your IQ is above 124.6728, then you're in the 95th percentile, okay? If you want to know what the 99th percentile is for IQ, it's 135, okay? And we can do it, you know, you can keep going if you want. What's the 0.999, 146, okay? And it keeps going. So you can see why Matlab says it's about 1, right, for integrating from negative infinity up to Einstein at 160. Okay, so you can use this, these 3 commands. We'll start at the beginning. Norm PDF, okay, norm PDF with the value that you're interested in computing the probability for, and the parameters of the distribution, parameters of the normal distribution. Norm CDF, the value that you're interested in, and the parameters of the distribution. That gives you the cumulative probability from negative infinity. The inverse CDF, the normal distribution, you have to give it the probability and the parameters, and it will compute the value of Z if you have 0, 1. If you have different parameters, it will compute the value at whatever percentile you've specified for the parameters that you've specified. Okay. Now, we don't just have to do that with the normal distribution, right? We can do this with the t distribution. So I can do TPDF, and then a value of, let's say, t is equal to 2, and the degrees of freedom, let's say we had a sample size of 30, so let's have 29 degrees of freedom. Okay, and we can compute that. It's about 6%. Okay, and if we do a t negative 2, about 6%. Okay, so not too far off of the normal distribution, right? T has fat tails, and you can check it this way, right? So let's say, we can also do the TCDF. Okay, and what we're going to do is say, what's the probability of same distribution, has the same degrees of freedom, and we're going to integrate from negative infinity to 2. It's about 0.9725, so very similar when we get up to this many degrees of freedom to the normal distribution. What's the to negative 2? Okay, it should be 1 minus 0.9725. Right? There we go. Okay, it's because of the symmetry. You can start to see that. So you can play around with this very nicely. We can also do the ICDF. This is one I haven't done with T, so we'll. Okay, we're back. Your professor has been doing too many of these little videos. So for the T distribution, ICDF, normal T distribution, comma, we need the probability, okay, just like it says right here, the probability P, let's say it's 0.95, okay, and now we're going to give the parameter of the T distribution 0.29. Okay, that's 0.29. That was my problem. 29 degrees of freedom. Okay, so the value at the 91st percentile of the T distribution at 29 degrees of freedom is 1.6991. Then that is exactly right. I chose one that I knew. Now, let's find out what it is for the 5th percentile. Okay, now remember the T distribution is symmetric. So if you know that the upper tail starts at 0.16991, okay, then 1 minus 0.95, the 5th percentile is going to be negative 1.6991. Okay, so we can find the T distribution at 2.5%. Okay, at 29 degrees of freedom. And you can see that's negative about 2 values of T, 2 standard errors below the mean. We can find the value above the mean. This is 0.975, right? Okay, and again, the symmetry will show you that it is positive 2.052. All right. So T, you can do exactly the same things. You can do, you better get away from all my mistakes here. We can do PDF, okay? And calculate the exact probability of getting some value of T given a T distribution with 29 degrees of freedom. We can do a CDF, getting the cumulative probability for that same value, okay? The cumulative probability integrating from negative infinity up to T. And we could do the ICDF, where we would take the integral, okay, that cumulative probability, and find the T value that corresponds to it to find the critical value. And you can see it's 2.0452, okay? And all we have to do is know the parameters. In this case, all we need to do is specify the degrees of freedom because T is a standardized distribution. All right, let me clear this. All right, now we don't just have to do normal or T, we can do binomial. So I can do binomial PDF to calculate the exact probability of a value. And here we need, let's say I have a sample size of 10, and I want to know what the a sample size of 10, and I want a probability. That's n right there, and I want the probability of each value to be 50%. Okay, so tossing a head 10 times, what's the probability of getting 5 heads? All right, the expected value. So what's the probability of getting 5 heads given 10 tosses of a coin, given it's a fair coin? Exactly to about a fourth of the time you'll get 5 heads. That's the expected value. It's the most probable thing, but you'll get it about a fourth of the time. Okay. Now, what's the probability of getting 9 heads out of 10, given a fair coin? Very low. It's about 1 in 100. That'll happen. So you can do the binomial PDF to get these specific probabilities. But if you want the cumulative probabilities, we would do binomial CDF. All I have to do is change that, right? And now I get the cumulative probability of from 0 to 9. So it's summing all the individual binomial probabilities that for x equals 0 to x equals 9, given I have 10 tosses of the coin, and given that the probability of landing heads or tails is exactly 0.05. And you can see that it's very unlikely to get 10 out of 10, right? About 1 in 1,000. It's very likely to get anything other than 1 out of 10, anything other than 10 out of 10, which is 9 heads or fewer, because it's summed from 0 all the way to 9. Now we can do the same thing. What's the CDF? We can change it from 0.05. Let's say it's not fair. Let's say it's like our the red solo cups, where we have let's say a 7% chance of having success. What's the probability of getting exactly 3 successes in 10 chances when we have a 70% chance of success on any trial? About 1%. Okay. What's the probability of getting 7 heads or 7 successes? Better type it in there. Okay. Anything up to 7 successes, and it's about 0.61. Okay. So we get those cumulative probabilities. So binomial PDF. Okay. Then we have the parameters of the sampling distribution of the proportion are n, right, the sample size, and p, the probability. And we can compute individual probabilities with binomial PDF. We can compute cumulative probabilities with binomial CDF. And I think we can also use ICDF. Let's try it. I keep screwing up on this one because I rarely use it. And this one we're going to use binomial. And then we're going to have the probability I want. Let's find the probability of 0.0106. I'm going to go backwards from this. Okay. Comma. Given I have 10 and 0.7. Oops. 4. Okay. So it's about the same as 3. So because 3 is very small. Is that right? The ICDF. So if I have a probability of 0.0106 given 10 and 0.7 chance of getting a success in each one, that will integrate to about 4. Okay. Because we start to get negligible differences over time. Okay, I can do ICDF comma, what's the probability of getting 0.25 given 10 tosses and 0.7. Okay, I'd expect about 6. Okay, expect about 6. The 6 heads has a probability of about 0.25. All right, and we saw that's the expected value. NP, about 0.7, okay, is the expected value. So this is a little less than the expected value. So its probability is going to be less than the expected value. All right, we can do it with hypergeometric. Okay, so hypergeometric is a little bit different, but we can do Hyg PDF. And here we have to give, Matlab uses different symbols than I do, but this is the value that we're interested in. Let's say we have a sample size, a population size of 100, okay, of which 20% are successes. And so we're going to say, what's the probability of getting 8 successes? Okay, the probability of 8 successes given samples of a population size of 100, given in the population 20 of those are successes, and given a sample size of 15. Okay, so we're saying population size, finite population size 100, about 20%, exactly 20% of the population, 20 items in that population are successes, or 20 events are successes. What's the probability of getting 8 successes in 15 trials? Very low, about 2 in 1,000. Okay, so we can do it with hypergeometric PDF. And again, if we change the parameters, we change the population size, we change the proportion of successes in the population, if we change the sample size, we can we can make this fit any hypergeometric problem that you have. But again, we tend to do intervals. So Hyg CDF. Okay, we can do, let's do 8, 100, comma 20, comma 15. So now this is going to give us the cumulative probability from 0 to 8. Okay, what's the probability of drawing anything between 0 and 8 successes, given I have a 20% probability of success from a population size of 100, and I've got a sample size of 15. About almost certain I'm going to get 8 successes or below. It's almost uncertain that it's very unlikely that I would get above 8. Okay? So I can do the CDF. There is no good way to do ICDF, the inverse CDF for hypergeometric. So I'm not going to go through that. It's very convoluted, and you don't need to worry about that. You can use these to compute with a little iteration to get to work from one side, from one probability backwards to the value that gives you that probability. There's also works for Poisson. And Poisson only has one parameter, the mean of the distribution. So let's suppose I have a, I want to know what's the probability of getting two successes, okay? Two particles hitting a particle detector given in a given interval of time, given that the probability of it happening in an interval of time is only about 0.01. So the average number, and yeah, so let's get lambda. Let's say we have an average of 5 particles hitting. Okay, what's the probability of getting 2? That's going to be fairly high. Yeah, about 8% for Poisson, and anything above that would be 92%. What's the probability of getting 5? About 18%. Okay, what's the probability of getting 16? Oh. Very small. Okay, it's highly unlikely if your average is 5 in an area of opportunity to get 16 in that area of opportunity in the same amount of time. Okay, so we can do Poisson, and that's the individual probabilities. That's the individual probabilities, again, PDF. I can do Poisson CDF. And get the cumulative probabilities. Oh, you're sorry. And that's about 61%. Okay, or 62%. Oh, doggone it. That's about 62. There we go, 62%. All right. And so we can do the CDF. Poisson. Okay, 16 successes. 1. Very, very, very. It's almost certain, almost completely certain. Okay, so we can do it the same way. We can do an ICDF. Poisson, we'll do ICDF. We're going to call it a Poisson distribution. And the probability, what's the probability of 0.3 in a Poisson distribution? Very low. But what's the value? 0.3. Okay, because Poisson only has the one parameter. We fixed it. Okay. Oh, let's see. So we've gone through all of them. We've gone through the normal distribution. We've gone through the t-distribution, the binomial, hypergeometric, and Poisson. And so you can use these, the PDF function, the CDF function, and the ICDF function to help you calculate probabilities, both individual probabilities and probabilities across a region. Okay, that's it. I hope this helps. Stopping the sharing, and let's record. There we go.